Welcome back everyone. In this lecture I will do the construction of all irreducible root systems, so that way we complete the classification. Okay. So, for each Dinkin diagram that we have seen earlier, so we are going to construct root system corresponding to that Dinkin diagram. So, I will leave most of the things for you to check, because these are all like just checking only. So, I will very explicitly construct. I will also tell you like how one can go about checking these things. So, most of the time we will be working inside Euclidean space and then taking elements from some lattice. So, some of the properties of root system will be obvious. Okay. So, what we do, we fix this Rn. Okay. So, this is where this is the Euclidean space with the standard inner product, and then we also take this epsilon 1 etcetera epsilon n to be the basis of this Rn, which is again standard orthonormal basis. So, this is standard orthonormal basis of Rn. So, now what we can do, we can just construct this lattice I, okay, which is Z span of all these epsilon i's. So, now note that if you take any elements from this I, then the alpha beta, the inner product will be always integer. So, then what you do, you basically you declare like if you want to construct a root system, you construct basically a subspace. So, here is the idea. So, to construct the root system that we are interested in, we first choose a proper subspace of Rn, and then a proper lattice. Proper in the sense not proper a subset, like appropriate subspace and appropriate lattice. So, then we take elements from that lattice which has some specified length. Okay. So, then phi will be defined to be those alpha from that lattice having some specific lengths. Okay. So, then by doing this, what we guarantee so many things. For example, if you take alphas that are having specific lengths, you avoid 0, that is fine. And then most of the time if you specify the lengths, then it is not hard to see the lattice elements will form a basis of the subspace that you are interested in. So, that first condition will be automatically satisfied. And the last condition, because your elements are coming from the lattice, the inner product will be always integers. So, by normalizing them, so you can always guarantee that the Cartan numbers are always integers. So, that property also will be satisfied. Then since you are specifically taking like some specific length elements, so whenever alpha is there, you can make sure that minus alpha is also there. And then if and only if minus alpha is there. Not only that, if alpha is there, multiple of alpha is there, then you can also easily check like that multiple must be plus or minus 1, that is also very clear. So, that will be again very clear by the choice. So, now if you are interested in verifying what will happen to the reflections, so then since you have very specifically specified the lengths, so that the reflections will actually take so the lattice will be invariant under the reflection, and these elements will have same length. So, once you apply the reflection, so that will actually guarantee you that reflections will leave this phi invariant. So, more or less all the properties of this phi will be like trivial to check. Okay. Once we specify which space you are working with and then which lattice you are working with. Okay. So, let us see some example, then only it will be clear what I am trying to say. So, this is the where we are working generally. You have some Euclidean space and then you start with this. So, you fix this epsilon I to be the standard orthonormal basis and I to be this z span of this epsilon I, which is the lattice. So, this is the standard lattice, okay, spanned by this epsilon I. So, now for example, how do you construct type A root system? Okay. So, type A, which we already did. So, let us do it again, where L is greater than or equal to 1. For this, you construct this Euclidean space as subspace of R L plus 1. You take this E to be orthogonal complement of this epsilon 1 plus etcetera epsilon L plus 1. You take this epsilon 1 plus etcetera epsilon L plus 1 and then take orthogonal complement of that vector inside your R L plus 1. So, this is has dimension L obviously, and this is the space in which our root system actually works. You take the lattice I dash to be just I intersection E. So, now it is clear that whenever alpha beta is in I dash, then the inner product alpha beta is an integer. So, that is trivial to check. Now, what is phi? So, phi is going to be those alpha in I dash such that the squared length of this or the inner product of alpha alpha is 2. Okay. So, this is our type A root system very explicitly. So, this is something you can check easily, not a problem, because since what we have specified, we have taken elements from the lattice. So, and these elements have very specific length, you can see that this phi lies inside compact subset of this capital E. Okay. And since you are intersecting that compact set with this lattice, so phi must be finite. So, that is obvious, and it is not hard to check. These are all the only elements that lies here. So, what are all the elements? You can just think about it. You can easily prove that this will be just plus or minus epsilon I minus epsilon j, where I ranges from I less than j from 1 to L plus 1. Now, it is not hard to see the one specific base is just epsilon 1 minus epsilon 2 etcetera epsilon L minus epsilon L plus 1. Okay. This consisting of L vectors. Okay. For example, if you take epsilon I minus epsilon j and then for I less than j, you can write epsilon I minus epsilon j to be just epsilon I minus epsilon I plus 1 plus etcetera plus epsilon j minus 1 minus epsilon j. So, that means this is in Z plus span of your pi. So, that means phi plus is nothing but epsilon I minus epsilon j, where I less than j. Again phi will be just a phi minus union phi plus. Okay. So, it is not difficult to see if you take this as base. Okay. So, then you list it as alpha 1 is epsilon minus epsilon 2 etcetera alpha L as epsilon L minus epsilon L plus 1. Now, using the inner product, you can see that alpha I inner product with alpha I plus 1. So, that is exactly equal to minus 1. Okay. So, now this is going to be your twice alpha I plus 1 divided by that alpha I plus 1 alpha I plus 1. So, that means this is the Cartan number alpha I plus 1. So, all other inner products will be 0. So, that is easy to see. So, that means the corresponding graph or the Dinkin diagram is exactly type A. Okay. So, all these are very clear. Now, naturally this reflection corresponding to this epsilon I epsilon j, this is acting on your capital E. Okay. Note that this reflection is going to fix this vector epsilon 1 plus etcetera epsilon L plus 1. Okay. So, in particularly you can actually extend this to the action of RL plus 1, there is no harm. You can extend this to action on RL plus 1. Okay. So, then you can easily see that if you take epsilon I minus epsilon j, and then if you apply it on any epsilon k, then this is going to be epsilon k if k is not I or j, and it is going to be epsilon I if k is epsilon j, and this is going to be epsilon j if k is epsilon I. So, basically the reflection epsilon I with respect to epsilon I minus epsilon j, it actually switches this epsilon I and epsilon j, all other elements will be fixed. So, basically it is a permutation that actually switches coordinates ith coordinate and jth coordinate. So, from this it is easy to see that the Weil group of this phi is indeed isomorphic to this SL plus 1, which is the symmetric group. So, I will leave it to check all the details. Okay. So, this is not very hard. So, now let us construct the root system B, type B. So, what is type BL, where L is greater than or equal to 2. Again we are specifically mentioning some particular L values, that is to avoid the repetition. Okay. So, here it is easy to define. So, you take E to be RL, not a problem, and then I to be your standard I. So, then phi is nothing but those alpha in I, where I is, recall, z span of the standard basis epsilon I. So, this is those alpha in I such that the squared length or the inner product alpha alpha is either 1 or 2. So, this is going to be your root system. So, now it is not hard to check very explicitly. So, what are all the elements in this root system? Check that this is exactly is plus or minus epsilon I union plus or minus epsilon I plus or minus epsilon j, where of course I not equal to j. So, they vary from 1 to L. Okay. So, in each cases you can calculate the cardinality of phi, you can calculate the cardinality of the Weil group and so on. Okay. I will leave it to you to check all those things. So, what is the base here in this case? In this case you can take base to be epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3 and so on, epsilon L minus 1 minus epsilon L comma epsilon L. So, this is the base for this phi. So, now why this is a base? It is not hard to see. You can write epsilon I as epsilon I minus epsilon I plus 1 plus etcetera plus epsilon L minus 1 minus epsilon L plus epsilon L. So, this is inside your positive roots phi plus. Okay. And similarly, you can see that epsilon I minus epsilon j. So, that is going to be when I strictly less than j, as before epsilon I plus 1 plus etcetera plus epsilon j minus 1 minus epsilon j. Again this is also going to be in your phi plus. Since epsilon I is already in phi plus, so that implies that epsilon I plus epsilon j, that is also in phi plus. So, you can see that these are all the only elements in phi plus. Okay. So, now in this case I will leave it to you to determine what is the Weil group. So, again you use the action of Weil group on this RL and then C. So, I already said how these reflections will act. So, as in the earlier type A case, you can see that the subgroup generated by these reflections will be just SL minus 1. Okay. So, now you have extra reflection that corresponds to epsilon L. So, you just compute how this reflection act on the basis epsilon I and then determine using that how the entire Weil group act on this capital RL, okay, capital E. Okay. So, I will leave it to determine. So, this is exercise, determine the while group. Okay. So, this is I will leave it. So, now what is CL? CL, as we said before, it is just dual of BL. So, you already know that what is the dual. So, dual of phi is nothing but phi check, which is alpha check, which is 2 alpha divided by alpha alpha, where alpha coming from phi. So, this is the dual. So, very explicitly, if you are interested in type CL, you can see that again we restrict L to be greater than or equal to 3 to avoid the repitance, because C2 is same as B2. You can take E to be RL, because the Euclidean space will not be changed. Now, phi will be those vectors inside your lattice I, such that now the inner product alpha alpha, either it has to be 4 because it comes from the dual, or it is 2. Okay, this is what happens. So, now you can very explicitly calculate, okay, either from the root system BL or from the definition, you can check that the elements of this root system CL given as follows. So, this is exactly plus or minus 2 epsilon I, where I ranging from 1 to L, union plus or minus epsilon I plus or minus epsilon j, where again I not equal to j, where I and j comes from 1 to L. Okay. Again, as before, the base, again the dual of the earlier base, which is epsilon 1 minus epsilon 2, etc., epsilon L minus 1 minus epsilon L to epsilon L. Okay. So, this is just the dual of the base that we had for BL. Okay. So, now again the while group of CL will be isomorphic to the while group of BL. So, in this case you can explicitly determine the action and then see there is a natural isomorphism between them, that I will leave it as exercise. Now, what is type DL? So, DL, it is given again very explicitly. So, the type DL, so where L has to be at least 4, you take again E to be RL. Okay. So, now you take phi to be those alpha in I, such that the inner product alpha alpha is exactly 2, and now it is again it is basically you can see that this type D is sitting inside type B as long roots, okay, and as well as it is sitting inside type C as short roots. So, then you can see that this is exactly explicitly plus or minus epsilon j plus or minus epsilon I and plus or minus epsilon j, where I not equal to j. So, it is not hard to see the base is exactly epsilon I minus epsilon 2, etc., epsilon L minus 1 minus epsilon L, comma epsilon L minus 1 plus epsilon L. So, now you can compute and then see what will be the Coxeter graph. For example, this will corresponds to Coxeter graph of the Dinkin diagram of A, because all of them have same root lengths. So, it is simply less. So, we do not need to worry about the Dinkin diagram. Dinkin diagram is same as Coxeter graph. So, this will form type A. So, you get something like this. Okay. So, here you have L minus 2, here you have L minus 1, here you have L. Now, you have to compute what happens to this. So, definitely this alpha L, it is going to be orthogonal to everything from 1 to L minus 2, sorry 1 to, sorry, here you have epsilon L minus 2 minus epsilon L minus 1, yeah, everything except L minus 3, up to this you will have. So, for L minus 2 you will have 1 each between this and this, okay. And if you compute inner product between alpha L minus 1 alpha L, you can see that that will be 0. Alpha L minus 1 and alpha L is exactly equal to 1 minus 1, which is 0. So, that means you get exactly the Coxeter graph of type DL. So, this is your L minus 2, this is L, this is L minus 1. Okay. So, this is DL Coxeter graph. Again, I will leave it to you to determine the while group action on this. Okay. So, that is again not that hard. So, the determining the explicit action of while group of the exceptional root systems, they are very hard actually, but for the classical types which are A, B, C and D, it is easy to determine the while group action. Okay. And note that all this A, B, C, D, they are infinite family of root systems, okay, and they are called classical types. So, we will see later that what are all the Lie algebras associated with this classical types at least. So, that can be very explicitly defined, okay, inside some general linear Lie algebra. Anyway, so let us now define what are these exceptional root systems. So, here like I said, it is easy to actually determine E6, E7 once you know E8, because E6 naturally sits inside E7 and E7 naturally sits inside E8. So, we will just give you the definition of E8 and I will just leave it you to find out what will be E7, E6 inside E8. So, you take your Euclidean space to be this 8-dimensional space. Note that E8 has rank 8. Okay. Now, what we do? We take this subgroup, okay, not exactly the lattice. I is already a lattice. Okay. This is just Z span of epsilon 1 etcetera epsilon 8. So, now what you do? You take I dash, which is just the subgroup, which is I plus Z of times this epsilon 1 plus etcetera plus epsilon 8. So, this is a subgroup of E, okay, because there are some rationals involved here. So, now what we do? We take another subgroup which is I double dash. So, this is the subgroup of I dash consisting of all elements summation C I epsilon I, where I range from 1 to 8 plus C by 2 epsilon 1 plus etcetera epsilon 8, for which the sum of the C I is always even and the C is coming from integers. Okay. So, it is not hard to check, this is actually a subgroup, okay, that is again I will leave it to you. So, it is very easy to check. Now, using this I double dash, we will define what is our root system, and again it is not that hard to check. If you take inner product between these elements, what it will be. Okay. So, you take your phi to be those alpha in I double dash such that the inner product of alpha alpha is 2. So, this is our root system. So, very explicitly again I will leave it to you to check, this is exactly equal to plus or minus epsilon I plus or minus epsilon j, where again I not equal to j varies from 1 to 8, union you take all this off sum of summation minus 1 power k of I epsilon I, where I range from 1 to 8, where this k of I either 0 or 1, but add up always even number. The sum is always even number modulo 2 0. So, this is what your root system E8. It is a bit complicated root system, but again but very explicitly given. Again, what is the base? Base is again bit complicated. So, but it is once I have told what is the base, it is easy to check it is a base. So, this is exactly half times epsilon 1 plus epsilon 8 minus epsilon 2 plus etcetera plus epsilon 7 and then comma epsilon 1 plus epsilon 2 minus epsilon 1, epsilon 3 minus epsilon 2 and then epsilon 4 minus epsilon 3, epsilon 5 minus epsilon 4 and epsilon 6 minus epsilon 5 and epsilon 7 minus epsilon 7. So, note that we have taken the same order that is there in the Dinkel diagram. Okay. So, the labeling is also like specified as before. So, that is the labeling we used. Okay. Maybe let me show you. So, this is our type E. So, this specific labeling, that is what we have. Okay. For that exact labeling, we have actually listed the elements of the base. Okay. Okay. So, now we have only two root systems are left, which is G2 and F4. So, let us define them, okay, and then I will stop. So, again if you actually, so using this action of W on this phi, one can actually get a formula for the cardinality of W. Okay. Again, it is an interesting exercise if you know the group action of business. Okay. So, it is not that hard to write down formula. For example, you can prove that the while group of this phi of E8. So, this has exactly cardinality 2 power 14 times 3 power 5 times 5 square times 7. So, this is the cardinality of E8 while group. Okay. Now, what is type F4? So, this is again you take 4 dimensional space, you take I dash to be I plus Z span of times epsilon 1 plus etcetera epsilon 4. So, then you take alpha in I dash. So, that is your phi such that the length of alpha, squared length of this alpha is either 1 or 2. So, this is the definition. Now, it is not hard to check that this phi is exactly equal to plus or minus epsilon I and then plus or minus epsilon I plus or minus epsilon j, where this I is not equal to j running over from 1 to 4, and then you have some more elements. So, which are just plus or minus of times epsilon 1 plus or minus epsilon 2 plus or minus epsilon 3 plus or minus epsilon 4. So, this is the root system, and the base will be epsilon 2 minus epsilon 3, epsilon 3 minus epsilon 4, and then epsilon 4 of times epsilon 1 minus epsilon 2 minus epsilon 3 minus epsilon 4. So, this is the base, and now you can easily check the Coxeter graph of this is exactly coincides with the Dinghen diagram of this is exactly coincides with Dinghen diagram of F4. Okay. And the one can show that the cardinality of the while group is also 2 power 7 and 3 square times 3 square. Okay. So, what is type G2? So, G2 you can see that it is a rank 2 root system. Okay. So, that means you have to find something inside rank 2. For that purpose, what we do, we take R3 and then construct this subspace inside R3. So, what is this subspace? You take orthogonal complement of this epsilon 1 plus epsilon 2 plus epsilon 3. So, this is your subspace inside R3. So, this is your Euclidean space of dimension 2. Now, what we do, we take again as before I dash to be I intersection E. So, then you take phi to be those alpha inside your I dash such that the length of this is either 2 or 6. So, this is very explicit root system. Again you can give this very explicitly. So, note that the length is either like squared length is either 2 or 6. Okay. That makes it okay. I will give you the positive roots. Okay. Negative roots are again easy to write. So, the positive roots are epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3, and then epsilon minus epsilon 3 twice epsilon 1 minus epsilon 2 minus epsilon 3, and then twice epsilon 2 minus epsilon 1 minus epsilon 3, and then twice epsilon 3 minus epsilon 1 minus epsilon 2. So, these are all the positive roots, and what is the base? base is epsilon 1 minus epsilon 2 minus twice epsilon 1 plus epsilon 2 minus plus epsilon 3. So, this is the base, and you can also prove the while group is actually very small group, it is 2 square into 3, 12 elements are there. So, I will leave it to you to check, okay, these are all the very explicit descriptions of root system, and these root systems corresponds to the types that we have already listed. Okay. So, this actually proves for each Lincoln diagram very explicit root systems are there. Okay. So, that actually completes the complete classification of irreducible root systems, and in particularly complete classification of finite root systems. Okay. So, we have proved a big theorem so far. Okay. Okay, I will stop here. I will continue with Lie algebras in the next class, because we now understood completely everything about root systems and their classifications. Okay, maybe some small details about like automorphism of root system and so on can be determined. Maybe we can do that in the one of the tutorials. Thank you very much.